Alright, so now I'm going to talk about the fundamental theorem of calculus part 2, which you will immediately notice is much more uh, frequently used than part 1. But before we dive right into that, I want to make a small tangent into antiderivatives. I've been talking about them briefly in the last couple of videos, but I never really talked about them fully. So I'll start with the power rule for antiderivatives. So the integral from u to the n of du equals u to the n plus 1 over n plus 1. So that totally makes sense, because if you take the derivative of this, you get n plus 1 to the u times u over n plus 1. These cancel, so you're just left with u to the n. Sorry, I forgot. Because you subtract by 1, and yeah. So, just to go along with how you should learn calculus, I will add a plus c to this. And I add the plus c because if you remember, the derivative of a constant is 0. So basically, this could be any number. And if I take the derivative of this, I would still get the this function right here. So that's why I have this plus c here. It's basically just the constant of integration. And if you don't have bounds on your integral sign, you need to put the plus c. I cannot stress that enough. If you forget it, you're going to lose points, just like for forgetting dx. So yeah, it's very important. And also, there are some trig integral formulas. So the integral of cosine of u. Oh no. The integral of cosine of u equals du equals sine of u plus c. So the integral of sine, the derivative of sine would be cosine, and the derivative of c would be 0. So that's why that rule works. And the integral of sine of u du equals negative cosine of u plus c, because the derivative of negative cosine is sine, and the derivative of any constant is 0. So basically, the derivatives of your 6 trigonometric functions that you learned earlier, if you take the antiderivative of those, you'll get the original trigonometric function. I'm not going to show those off in the video just because, you know, it's pretty obvious for you to find yourself, and I'm losing my breath, but I included them in the handout. So in case you can't think to do the reverse process, it'll be there for you. So now on to the second part of the fundamental theorem of calculus. If your function f is continuous on the interval a to b, and if f is a derivative, is any antiderivative, sorry, I can't read my handwriting. If f is the antiderivative of little f for the interval, then the integral from a to b f of x dx equals the antiderivative of b minus the antiderivative of a. So before I talk about the significance of this theorem, I'll just give an example using the power rule for integrals that I just showed you. So let's say we're asked to find the integral from negative 1 to 3 of x cubed plus 1 dx. So using that cool power rule and the sum rule, we can find the antiderivative. So the antiderivative of x cubed is x to the 4th over 4. So the derivative of that would be x cubed, so that's why it's the antiderivative. And the antiderivative of 1 is x. So I draw this line to show what I'm evaluating it at, and that'll be from 3 to negative 1, and that equals f of b, big F of b, minus big F of a. So I evaluate the antiderivative at the upper bound, 3, and subtract it from the lower bound, -1. So the antiderivative at the upper bound is 3 to the 4th, which is 81 over 4, plus 3 minus -1 to the 4th, which is 1 over 4, minus 1. So just doing the math, I would get, let's see, 93 over 4 plus 3/4, 96 over 4, which equals 24. So yeah, basically I just took found the integral of a function for a certain certain bounds by hand. I didn't need to graph it. I didn't need to use some silly approximation or my calculator, and just to verify with my calculator, if camera will let me, of course. The math 9 -1 to 3. I'm terribly sorry about this. -1 to 3. Oh no. -1 to 3 of x to the 4th, no, x cubed, plus 1 dx is 24. So you can do any, well, not any, you can take you can evaluate a lot of functions by yourself, and in the day before calculators were invented, this was how you would find your definite intervals. So if you'll notice, right now, what I've put on my handouts for antiderivatives, what you have now is very limited. Polynomials and trigs. So in the next couple of videos, I'm going to be showing you some more techniques that you can use to calculate antiderivatives. So until then, bye.